All right, today we're diving into something called cognitive load. It's this fascinating idea that explains the surprising reason why just practicing over and over again doesn't always make you perfect. We've all heard that saying a million times, right? Practice makes perfect. It's basically lesson number one in how to get good at anything. But what if it's not the whole story? What if some kinds of practice actually get in the way of learning? So, let's talk about the problem with practice. It turns out, way back in 1988, a new idea started to challenge everything we thought we knew about how we learn. In a paper from that year, a psychologist named John Sweller dropped this bombshell of an idea. He said that for some problems, the very act of trying to solve them can actually interfere with learning. Now, think about that for a second. The effort you're putting in to find the answer might actually be stopping you from understanding the how and the why. It's a huge puzzle. How could that possibly be true?
Well, the key to this whole puzzle is a concept that Sweller helped make famous: cognitive load. You can think of it as your brain's bandwidth. And, just like your internet, it definitely has its limits.
So here's the deal. Your working memory, which is the part of your brain that's juggling all the new information you're taking in, it's not infinite. It's got a pretty tight capacity. Cognitive load is just the fancy term for how much of that limited mental workspace you're using at any given moment. Probably the best way to picture this is to think of your brain as the RAM in your computer. You know what happens when you have way too many programs and browser tabs open at once, right? That's a high-load task. The whole system just slows to a crawl, things get laggy, and it has a really tough time saving anything new. But when you're just running a couple of simple things, a low-load task, everything is snappy, smooth, and saving new info is no problem at all.
Okay, so that raises a question, right? What exactly makes a task high load for one person, but maybe low load for another? A huge part of the answer is in the really cool difference between how an expert and a novice actually think.
So when a novice, a beginner, tackles a problem, they usually use something called means-ends analysis. Basically, they start with the goal, the end, and then they try to work backward. It forces them to constantly juggle where they are, where they need to be, and all the possible steps in between. It creates a ton of cognitive load. Experts, on the other hand, they do the opposite. They use what's called a schema-driven strategy. They look at the problem, they recognize the type of problem it is, and then they just work forward using a mental model they've already built. It's way more efficient and a much lower cognitive load. And here's another key difference. If you ask a novice to sort a bunch of physics problems, they'll group them by the surface stuff. They'll put all the problems with a ramp or an inclined plane in one pile. But an expert, they see right through that. They see the deep structure. They'll group problems based on the fundamental principle at play, like the conservation of energy, even if one problem is about a pendulum and another is about a roller coaster. And this is the real heart of the problem for the beginner. That whole backward-working strategy is so mentally demanding, it just maxes out their cognitive RAM. Every ounce of their mental energy is being spent just trying to find the solution. There is literally no bandwidth left over to notice the underlying pattern and build those mental models they need to actually become an expert. Now, this was an amazing theory, but, a theory is just a theory until you can prove it. And that's where Sweller designed this incredibly clever goal-free experiment to see if easing up on the pressure to find a single specific answer could actually help people learn better. So here's how he set it up. He took two groups of students and gave them all the same tricky geometry problems. The first group, the conventional group, got a very specific goal, like find the length of line X. But the second group, the goal-free group, got a much vaguer instruction. They were just told, find the values of as many lines and angles as you can. The real test wasn't solving the problems, though. It was what happened after, when he tested how well they actually remembered the structure of the problems they'd just worked on. Okay, so what do you think happened? I mean, the obvious question is, who was faster? The group with the super clear, focused goal, or the group that was just kind of exploring the problem? Well, this is what's so fascinating. When you look at their speed, there was almost no difference at all. Both groups started at about the same time, they both got faster as they went on, and they ended at roughly the same speed. If you were only measuring performance, you just shrug and say, well, both methods work about the same. But see, performance was never the real test. Sweller wasn't interested in how fast they were. He wanted to measure what they learned. The really crucial question was about what they actually retained and moved into their long-term memory. And the results here, honestly, they're just staggering.
When he tested their memory of the problems, the conventional group, the ones with a specific goal, made more than double the errors of the goal-free group. The difference in what they actually learned was absolutely massive. So let that sink in for a second. Even though their performance on the task was basically identical, the students who weren't laser-focused on one specific answer ended up understanding and remembering the material far, far better.
So what does all of this actually mean for us? When we're trying to learn something new and complex, how do we use this to learn smarter, not just harder?
It all comes right back to our brain's bandwidth. The goal-free group wasn't wasting precious mental energy constantly checking, am I getting closer to the answer? What's the next step to get to X? By removing that mental tax, they freed up a whole lot of cognitive space. And what did they do with all that extra mental RAM? Well, they could actually pay attention to the relationships between the different parts of the problem. They had the space to see the patterns, to get the bigger picture, and to start building those mental blueprints, those schemas that are the true foundation of real expertise. So let's just boil this all down. First, remember your working memory isn't infinite. When you're new to something, typical problem solving can totally overload it, and that, ironically, stops you from learning. The secret, then, is to find ways to lower the mental load that isn't absolutely essential. Try to shift your focus away from just racing to find the one right answer, and instead, give your brain the space it needs to really understand the process itself. Which kind of leaves us with one last big question to think about. When it comes to real, deep learning, what if getting to the goal isn't really the point at all?